Earth is the cradle of humanity, but one cannot live in the cradle forever. Those words were written by the Russian rocket pioneer Konstantin Tsiolkovsky in 1911, more than half a century before a human being first left the ground and reached orbit. He had no rockets capable of reaching space, no computers, no materials, science capable of building a heat shield. Na rupper mesher, rakaber mauber, daber meisaber mauer, ray. And yet he understood something profound about the long arc of human destiny. The cradle is not the destination, it is the beginning. Everything humanity has ever accomplished in space, every satellite launched, every spacewalk conducted, every science experiment floated in microgravity, every astronaut who has looked back at the Earth from the window of the International Space Station. All of it has happened within a fragile shell, only a few hundred kilometers above the surface of the planet where we were born. Low Earth orbit, the region where the ISS circles at roughly 400 kilometers altitude, is so close to the surface that if you scaled Earth down to the size of a basketball, the station would orbit less than the thickness of a postage stamp above the ball. For more than 60 years, that postage stamp has been the boundary of continuous human presence in space. The next chapter of exploration is about crossing it permanently and heading somewhere that actually requires leaving Earth behind. That next chapter begins not with Mars and not with the stars, it begins with the Moon. And it begins with a question that sounds simple but carries enormous consequences. Can we learn to live somewhere other than Earth? The answer to that question will be written on the surface of the Moon over the next decade, and the writing has already started. NASA's Artemis program has been building toward the return of human beings to the lunar surface since the early 2020s. The first uncrewed test of the full Space Launch System rocket and Orion spacecraft, Artemis 1, flew in November 2022 and validated the architecture. Then on the 1st of April 2026, Artemis 2 lifted off from Kennedy Space Center's Launch Complex 39B and made history. 4 astronauts became the first human beings to travel beyond low Earth orbit in more than 50 years. Flying a free return trajectory around the Moon and splashing down safely on April 10th. The mission did not land on the lunar surface. It did not need to. What it needed to do was prove the SLS Orion stack could bring them home safely. It was the shakedown cruise before the main voyage, confirming that the machinery works and the people inside it can survive the journey. The path to the actual lunar landing has taken longer than originally hoped. Hydrogen leaks and integration challenges pushed the timeline forward. Artemis 3 was restructured in early 2026 into a low Earth orbit demonstration flight, designed to validate commercial lander docking. The first actual crewed lunar landing was shifted to Artemis 4 with a target of early 2028, according to NASA Administrator Jared Isaacman. These delays are frustrating, but not surprising. Apollo took years of incremental missions before Neil Armstrong and Buzz Aldrin touched down. And the systems involved in returning to the Moon in the 2020s are far more ambitious in their long-term goals than Apollo ever was. The landing system for Artemis is SpaceX's Starship, and understanding what Starship represents requires understanding why it is different. Every rocket ever launched before Starship was, at some fundamental level, disposable. You built it, you fueled it, you flew it once, and you threw it away. Imagine if every commercial flight required manufacturing a new airplane from scratch and then scrapping it after landing. The cost would be astronomical, the flight rate would be glacial, and no airline could sustain the economics. Starship is designed to be flown thousands of times, refueled and relaunched like an aircraft, with both stages returning for rapid reuse. By May 2026, the vehicle had completed its 12th integrated flight test, demonstrating progress toward full booster catch and upper stage recovery. Starship is engineered to carry between 100 and 150 metric tons to low Earth orbit. compared to roughly 95 metric tons for the SLS Block 1. When combined with orbital propellant transfer, its capability becomes transformative. Reusability changes the economics of space access the same way reusable aircraft change travel. It turns a rare event into something routine. The reason the moon matters so profoundly to everything that follows comes down to one thing: water ice. The South Polar region contains permanently shadowed craters where temperatures drop below -170 degrees Celsius, preserving water ice for billions of years. NASA's LCROSS mission confirmed the presence of water ice in 2009, and India's Chandrayaan-1 provided additional evidence from orbit. This ice is not just interesting scientifically, it is the key to making the moon self-sustaining. Water can be split into hydrogen and oxygen, providing rocket propellant for future missions and breathable air for the people living there. The same water can supply drinking water and support plant growth. Instead of launching every drop of water from Earth at enormous expense, a lunar outpost can eventually manufacture what it needs from local resources. This is the concept called in situ resource utilization, and it is the principle that makes any long-term human presence beyond Earth economically viable. In March 2026, NASA Administrator Jared Isaacman announced that the agency was pausing the Lunar Gateway and redirecting resources toward a sustained crewed surface base. Isaacman's decision accelerated the path to the surface and focused resources on what the program ultimately needed to demonstrate. While NASA is building its path back to the moon, China and Russia are building their own. The International Lunar Research Station program envisions a permanent outpost, constructed through a series of missions in the 2030s using China's Long March 9 rocket, a super heavy vehicle targeting 150 metric tons to orbit. China has already demonstrated impressive capability. In June 2024, the Chang'e 6 mission completed the first-ever sample return from the lunar far side. Chang'e 7 is targeted for launch in late 2026. Chang'e 8, aimed for 2028, will demonstrate in-situ resource utilization, including 3D printing of structural components. Think of Artemis and ILRS as two teams racing to build the first permanent camp on a new continent, each one pushed to move faster. Commercial lunar landers under NASA's CLPS program have been proving the logistics. Intuitive Machines' Odysseus achieved the first commercial landing in February 2024. Firefly Aerospace's Blue Ghost lander touched down successfully in 2025. These missions are establishing the supply chain for permanent human presence. The International Space Station will deorbit around 2030 to 2031, ending a continuous human presence in low Earth orbit that began in November 2000. But the transition to commercial stations is already underway. Axiom Space, VAST, Blue Origin, and Voyager Space are all developing new platforms. The launch vehicle landscape has transformed. Blue Origin's New Glenn achieved its first orbital flight in 2025. Vulcan Centaur and Ariane 6 are operational. This combination of massive rockets creates a launch cadence and economics that make everything in the following chapters physically possible. Part 2. Robotic scouts, tasting oceans, flying alien skies, and reading the universe. While human crews are establishing their foothold on the moon, robotic emissaries are already pushing far beyond it. They go first, they take the risks that would kill a crew, they return data across billions of kilometers, and they answer the questions that make human decisions possible. The largest robotic mission NASA has ever launched is currently on its way to Jupiter. Europa Clipper lifted off on a SpaceX Falcon Heavy in October 2024. On March 1, 2025, the spacecraft flew within 884 kilometers of Mars, using the planet's gravity to reshape its trajectory and pick up speed. It will perform a second gravity assist at Earth in late 2026 and then head outward toward Jupiter, arriving in April 2030. Once in the Jovian system, Europa Clipper will execute 44 close flybys of Europa over 4 years, approaching as low as 25 kilometers above the surface. Its ice-penetrating radar will sound through the ice shell and map the ocean boundary. Its spectrometers will search for gases from possible water plume sources. The mission's purpose is to fly through the spray above the ocean wave, gathering information to characterize whether the hidden ocean could support life. Europa's ocean is estimated to contain twice the total volume of all Earth's oceans combined. If that ocean is habitable, it would be the most significant discovery in history. While Europa Clipper heads to Jupiter, another mission is preparing to do something that has never been done. Dragonfly is a rotorcraft lander for Saturn's moon Titan. It will fly through Titan's thick atmosphere, hopping from site to site like a robotic helicopter scout, exploring an alien world from the air. Titan is larger than Mercury, with surface atmospheric pressure 1.5 times Earth's sea level and lakes and rivers of liquid methane and ethane. Its upper atmosphere is a factory for complex organic chemistry, producing molecules called tholins that rain down into vast orange dune fields. Dragonfly is targeted for launch no earlier than July 2028. After a 6-year cruise, it will arrive and spend 3 years exploring the surface. It will land at the Shangri-La Dune Field and later fly to the Selk Impact Crater, where ancient meteorite impacts briefly melted water ice and mixed it with organics. That environment could have hosted prebiotic chemistry, the kind of molecular bootstrapping that may have preceded life on early Earth. As Elizabeth Turtle described it, Dragonfly will search for the building blocks of life in an environment that may resemble the early Earth. The most painful story in current robotic exploration is the fate of Mars sample return. For decades, scientists have argued it is the highest priority mission. Perseverance has been drilling and sealing rock samples since 2021, and more than 20 of those tubes are now sitting on the surface, waiting. In January 2026, the primary NASA ESA Mars sample return architecture was canceled due to costs potentially exceeding $10 billion. The samples are still there. The science waiting inside them has not changed. Ambition in space must be matched by sustained commitment in funding. Beyond the solar system, a revolution in telescope capability is transforming our ability to study the universe. The Vera C. Rubin Observatory is leading the way. It is repeatedly imaging the entire southern sky, building a time-lapse movie of the variable universe, discovering supernovae and tracking asteroids. When a previously undetected asteroid is found to intersect Earth, early warning is the only defense, and Rubin is the most powerful warning system ever built. The extremely large telescope, with its 39.3-meter primary mirror, will be the largest optical telescope in the world when it achieves first light in the late 2020s. Its light-gathering power and advanced adaptive optics will enable it to directly image planets around nearby stars and analyze their atmospheres. This is the capability that could, for the first time, detect the spectral signatures of oxygen, water, or ozone in the atmosphere of a rocky planet orbiting another star. NASA's Nancy Grace Roman Space Telescope, targeted for launch around 2027, will test the coronagraph technology needed to find habitable worlds. In space, the European Space Agency's LISA will extend gravitational wave astronomy. 3 spacecraft will measure the tiny stretching of spacetime. LISA will detect the mergers of supermassive black holes across billions of light years. No electromagnetic telescope can see these events. LISA will hear them. ESA's JUICE spacecraft is traveling toward Jupiter and will enter orbit around Ganymede in December 2034, orbiting a moon other than our own. NASA's NEO Surveyor will expand the asteroid catalog. CMB-S4 will map the cosmic microwave background with unprecedented sensitivity. The Square Kilometer Array will begin operations in the late 2020s, opening new windows on the early universe and cosmic magnetism. And the 2023 Decadal Survey has designated a Uranus orbiter and probe as the highest priority flagship mission, the first since Voyager 2. Together, these instruments are doing something unprecedented. They are equipping humanity with the sensory range to finally answer the question of whether life exists elsewhere in the universe. Welcome to the new age of exploration. Imagine being locked inside a small studio apartment with 5 other people. You cannot open the windows. You cannot step outside for even a moment. The walls do not change, the view does not change, and the same 5 people are around you every single day. Now imagine that arrangement lasting not for a week or a month, but for 9 months, with another 9 months on the return journey and a 500-day stay in the middle, totaling somewhere between 2 and 3 years away from Earth. No fresh air, no natural environment, no ability to call home and have a real-time conversation, because even at the speed of light, the gap between you and everyone you know grows to between between 4 and 24 minutes each way. That is what a human mission to Mars actually involves for the people inside it, and being honest about that reality is the only foundation on which a serious mission can be built. Mars sits between roughly 55 million and 400 million kilometers from Earth, depending on where the two planets are in their orbits. A standard Hohmann transfer trajectory, the most fuel-efficient path between the two planets, takes between 6 and 9 months one way. Because Earth and Mars only align in the right configuration roughly every 26 months, a crew that lands on Mars during one alignment must wait approximately 500 days on the surface before the planets align again for the return journey. The total mission duration for the first human Mars expeditions is therefore likely to fall between 900 days and just over 1,000 days, roughly 2.5 to 3 years. NASA's Moon to Mars architecture documents lay out a stepwise approach in which lunar experience directly informs the development of Mars transit, landing, and surface systems. Internal NASA planning horizons point to the 2030s or 2040s, depending on funding trajectories and technology readiness. SpaceX has repeatedly stated targets for the late 2020s. Realistic assessment suggests the mid to late 2030s as the most probable window, accounting for propellant transfer and life support validation. The radiation environment on the journey to Mars is one of the most serious medical challenges. Galactic cosmic rays and solar particle events are intense threats. The Earth's magnetic field and atmosphere provide substantial shielding, but in deep space, these threats are present at full intensity. NASA estimates for an unshielded round-trip mission suggest a dose exceeding 1 sievert, a 5% increase in the lifetime risk of fatal cancer. Mitigation strategies include water walls, polyethylene panels, and storm shelters packed with supplies in the center of the spacecraft. Each reduces the risk to levels considered manageable for a crew of highly motivated professional astronauts who have accepted the risk profile. Physiological challenges include bone mineral density, decline of 1 to 2% per month, and muscle atrophy despite vigorous countermeasures. Spaceflight-associated neuroocular syndrome can cause measurable changes in vision and structural changes in the eye that may not fully reverse. Mars' surface gravity is 38% of Earth's. Whether this is sufficient to prevent bone and muscle loss remains an open medical question. A crew confined for years will face interpersonal dynamics, cognitive fatigue, and the weight of knowing no rescue is possible. If a serious medical emergency occurs on the Martian surface, the crew cannot be extracted. Earth is minutes away via radio. The surface base must function as both a home and a factory, using inflatable extensions and Martian regolith for radiation shielding. The base must produce its own propellant. The Sabatier reaction combines Martian CO2 with hydrogen to manufacture rocket fuel. NASA's MOXIE instrument successfully produced oxygen from Martian carbon dioxide, proving the core chemistry works in the real environment. Every breath of air and watt of heat requires continuous power. Mars experiences global dust storms that can end solar missions. Small fission reactors offer power independent of sunlight. NASA's crusty demonstration proved these compact systems can operate reliably. Terraforming Mars is not feasible with currently foreseeable technology. There is not enough accessible carbon dioxide to thicken the atmosphere. The more realistic path is paraterraforming, building large enclosed pressurized habitats and domes within a hostile environment. After Mars, what comes next? This final part is about the technologies that could one day take humanity to the stars. The Habitable Worlds Observatory is NASA's aspiration for the 2040s, designed to directly image Earth-like planets orbiting distant stars. If it detects the spectral fingerprint of a living biosphere on even one other world, it will be the most transformative scientific discovery in history. Nuclear thermal propulsion could cut the Mars transit time to 3 or 4 months, drastically reducing radiation exposure. Breakthrough. Starshot is developing technology to accelerate tiny spacecraft to 20% of the speed of light using ground-based lasers. At that speed, a spacecraft would reach Alpha Centauri in 20 to 25 years. It is like using a flashlight to push a butterfly across an ocean. Interstellar precursor missions will sample the medium beyond our solar system. Voyager 1 and 2 continue to drift, carrying humanity's message. All this requires an economy that can sustain it. Asteroid mining and satellite constellations are driving a $1 trillion space economy. The Kardashev scale classifies civilizations by their energy use. Humanity is currently at 0.7, just beginning to access solar resources. Look again at that dot. That is here. That is home. That is us. The image underscores our responsibility to deal more kindly with one another. The overview effect is a cognitive shift from seeing the planet as a whole, a borderless world with nothing to protect it but its own conditions. The choice between cherishing the pale blue dot and reaching for the stars is not a choice between opposites. We must do both. We cannot live in the cradle forever, but we must cherish it as we leave, remembering that the pale blue dot is the home we are extending.